Okay, hi guys, and in our past two videos we've looked at the sine rule, and today we are going to look at the cosine rule. So now, according to the cosine rule, this is what we have. It says that in any triangle, in any given triangle, which we'll call triangle ABC, let's name this ABC, right? Remember, this side is small a, the one opposite b small b, the one opposite c small c. This one works with side angle side. You always need a side and angle in a side, right, in order to use the cosine rule. Which means if I'm looking for this side, which is a, if I'm looking for a, I must have that side, that angle right there, and that side. So this is how you set it up. You are going to say a squared is equals to that side squared, which is b squared, plus that side squared, which make up the side angle side, minus 2 times a product of these two, which is b and c, and then cosine of what? Cosine of the included angle, which is a, right? Which means now if we are looking for the side b, we must also have a side angle side. So the side has to be this one, the angle has to be this, and that side as well. So it means that b squared has to be equals to a squared plus c squared minus 2 into a product of these two, which is a multiplied by c, cosine of what? Cosine of the included angle, which is b, right? So again, in order to use the cosine rule, you need a side and included angle and another side, which means now if we are looking for the other side now, which is c, if we are looking for c, we must have this side, that angle, and that side, which means c squared has to be equals to a squared plus b squared minus 2 into a multiplied by b, cosine of the included angle, which is cosine of c. As you can see, that is summarized there, right? A squared is equals to b squared plus c squared, just like we said, minus 2bc cosine of a, and b squared, and so on. Right, now we are going to jump into the proof of the cosine rule. Right, so we are required to prove what? We are required to prove that c squared is equals to a squared plus b squared minus 2 into a multiplied by b, cosine of what? Cosine of c, right? Cosine of c. So this is how we're going about that. Let's say we have a triangle. We have an acute angle triangle, assuming this is an acute angle triangle with this side a, b, c, and then we said this is small a, this is small b, and this is small c. First of all, we need to construct, right? So we are going to construct AD again, right? We are going to construct AD such that D lies on what? Lies on BC, and also that AD should be perpendicular to BC. So what we have now is a perpendicular height that runs all the way from A to there, which we'll call this D, and then we said this should be perpendicular, and then we are going to let something. We are going to let AD equals to H, right? And then after letting AD equals to H, we then have that let CD or DC equals to X. So we are going to let this side equals to X, but remember that the whole of BC is that side A. Now since we have DC or CD as X, it means this side BD has to be A minus X. It's the total of that side minus this small portion to get that one, right? And now moving forward, we are going to apply the Pythagoras theorem on either one of these two right angle triangles. So the first one we have is that one. We have this right angle triangle, which is orientated like that, whereby here we have A, we have D. Remember this side is A minus X. We have B here, and then we have C, we have H, right? So when we apply the Pythagoras theorem, we have that the side c squared has to be equals to the side A minus X all squared plus H squared, and this is according to the Pythagoras theorem, right? And then from here we have what? We have c squared. When we expand this, remember we are going to open two brackets, and when we expand we are going to get a squared minus 2ax plus what? Plus x squared plus h squared, right? I would like to group these two. Can we group the h squared and the x squared together so that we have c squared, which is equals to, we have a squared plus, let's keep this as x squared plus h squared, then we keep that as minus 2ax, right? That's our first equation. So now we are going to apply the Pythagoras theorem on the other triangle, right, which is orientated like that. Now it's the other piece, which is like this. Now remember, we have this as a, we have d here, we have x, this side is h, we have c, and then we have b, right? So when we apply the Pythagoras theorem, we are going to have that b squared now, which is the hypotenuse, is equals to h squared plus x squared. So it's the sum of squares on the other two sides, right? But now if you look at this, the h squared plus x squared is what we have there, which means now we can take this equation 2 and substitute into that. When we substitute it into that, which means now we have c squared, which is equals to a squared. Wherever we see x squared plus h squared, we write it as what? As b squared. So this is a squared plus the whole of that, which is b squared minus 2ax, right? Now we move, let's move forward. But then what we are trying to prove doesn't have that x there, doesn't have the x. So we are going to try to find an expression for x using that triangle right there, because it's the one that contains x. So let's apply cos, let's apply the cosine of c there. When we say cos c, remember that cos is adjacent over hypotenuse, so the adjacent is x divided by the hypotenuse, which is b. Making x the subject of the formula gives us that x is equals to b cosine of what? Cosine of c. Then we are going to go straight into that. So we are going to substitute the x that we just found back here. So now we are going to have the expression as c squared, which is equals to a squared plus b squared minus 2a. Wherever we see the x, we just substitute what? B cosine of c. So that's how you prove the cosine rule for c squared. Of course, in order to prove for the other angles, you just need to change the way in which you bisect or you cut your triangles. Let's say if you want to prove for a squared, then it has to run through AB. In order to prove for the other one, it has to run through what? Through AC, starting from B. Or when you have this works for acute angle triangles. Whenever you have an obtuse angle triangle for that looks like this, right, whereby this is A, this is B, and this is C. Remember, this is small b, this is small c, this is small a. Now your construction should run from A. You are going to construct a perpendicular height there, which is AD, such that this is perpendicular to that, and you are going to let this equals to h. When you let that equals to h, this side, let this side equals to x, and let this one is just going to be what? If you let this one equals to x, yeah, let this side equals to x, which means now the whole of that triangle there, the whole of BD has to be a plus x now. That's the total length of that, which means now you are going to have two right angle triangles. The first one is going to look something like this. It's going to be that triangle which is A, B, D, whereby this side is a plus x, you have this side as h, you have that as c. And then the other right angle triangle, which is like that, whereby now you have this as x, you have this as a, you have this as d. Remember, these are both right angle triangles. This is c. But then if you look at this, the c is this angle right here, which means the inner one, this one has to be 180 degrees minus c, right? Yeah, and this side has to be our b, then we have h there. So if you follow the steps that we just did previously, it should come out nicely, right?